Welcome to the CompTIA A+ 220 1101 or Core 1 exam. This is Objective 3.3, RAID. It's not uncommon to use hard drives to store large amounts of information. Terabytes upon terabytes of data can be stored on the single spinning drive. And of course, because there are moving parts inside of these drives, they will eventually fail. Fortunately, there are things you can do so that when a drive fails, your data will always remain available. And in this video, we'll look at how RAID arrays can be configured to provide this type of data redundancy. As we go through the video, it may seem that RAID would be a very good way to back up your data. But the data in a RAID array is not a copy of your data. It is the data that you are actively retrieving or storing. And because of that, you have to keep in mind that RAID is not a method of backup. It's simply a way to maintain uptime and availability if one of those drives happens to fail. The term RAID is an acronym for Redundant Array of Independent Disks. Earlier versions of this acronym used the word inexpensive disks instead of independent, but it's effectively the same idea. We can use multiple storage drives in a system that work together to maintain this uptime and availability. There are different types of RAID. We refer to these different types as RAID levels. And although the name is Redundant Array of Independent Disks, there are some RAID levels that do not provide redundancy. So you have to be very careful when you're initially setting up your RAID array, that you're choosing the right RAID level. Let's step through each of these RAID levels to see how they might be used. And we'll start with the RAID 0 or striping. We refer to this as striping because we have at least two drives in a RAID 0 array. And instead of writing everything to one drive or everything to the other drive, we take all of our data and we split it evenly between these two drives. So let's take the example of a file that exists on 8 different blocks. And we have disk 1 and we have disk 2. The single file will be split evenly between these two disks. So block 1 is on disk 1, block 2 is on disk 2, block 3 is back at disk 1, and block 4 is over at disk 2. So you can see that distributing this across multiple drives provides a performance increase because we only have to write or read half of the data if we have two separate drives. But one of the problems with that is if we lose one of these drives, none of the data will now be available because you're effectively lost half the data that you've stored. You should always think that RAID 0 is the same thing as having zero redundancy. That's kind of the running joke. Okay, let's take a look at RAID 1. RAID 1 looks very similar to RAID 0 in its structure, but it's not. You can see that there's disk 1 and disk 2. However, with RAID 1, we are duplicating data between both of these drives. So each drive effectively is a mirror image of the other. That's why we refer to as RAID 1 as mirroring. You can obviously see in this scenario that if we are using twice much drive space than we would with RAID 0. Because we are duplicating every single file, we will effectively need twice as much storage to be able to store the same amount of information. But on the plus side, if we lose either of these physical disks, our data remains available because we have an exact duplicate of that data on the other disk. It's not uncommon when working with a RAID array that you would lose a drive and not even realize it until you receive an alert or a message that the drive has failed. Instead of duplicating every bit of data that you're storing on these drives, there is a more efficient method. That method is RAID 5, which we call striping with parity. This is the same as RAID 0, where we take all of the information that we're storing and we put pieces of that data across different drives. But unlike RAID 0, which of course has 0 redundancy, we have an additional drive where we store some parity information. That parity information allows us to rebuild the data if we happen to lose any of these physical drives. This is a much more efficient use of drive space because you have all of the data being stored across drives and then on one additional drive, some parity information. So if you're storing this on 4 separate drives, 3 of those drives can be used for data and 1 of those drives can be used for parity. As you can see from our example, we also distribute the parity to different drives, which helps during the recovery process. And that recovery process is important when a single drive fails in that RAID 5 array. It may seem that losing a single drive will also cause some of our data to be lost. And although that's true, we're able to rebuild this data in real time by taking advantage of the parity information that we have stored separately. Having to recalculate this data in real time based on the parity that's left over could cause a performance hit because the CPU cycles required to do that are intensive. But with the proper processing on the RAID controller and the proper CPU inside your system, you may not even see that much of a performance lag or bottleneck at all. And the last RAID type we will look at is RAID 10. Some people refer to this as RAID 1 plus 0, or a stripe of mirrors. Let's go back to the original RAID 0 configuration, and in this example we have RAID 0 with 3 separate physical drives. And you can see that we are evenly distributing our files across all 3 of those individual drives. As with RAID 0, if we lose any of those drives, then all of our data is inaccessible. So with the RAID 1 plus 0, we add on the RAID 1 part of the mirroring aspect, and we start mirroring all of our RAID 0 arrays. So now we're still storing these separate stripes of data, but instead of only having 1 copy of the stripe, we are mirroring each of those stripes of data. That way, if we lose any of these drives, we're still up and running because we have an exact duplicate of that stripe. And in our example, we could even lose 3 separate drives and still have access to all of our data, as long as the 3 drives that we're losing are part of the single pairs in each individual one mirror. We are at the end of Objective 3.3. Here's a pop quiz. Which RAID storage technology has the least amount of redundancy? A. RAID 0, B. RAID 1, C. RAID 5, or D. RAID 10? And the answer is RAID 0. RAID 0 does not offer any redundancy. If one of the disks fails, you will lose all of your data. Thank you for watching.